Welcome friends, Igor is here, and in this video we will discover some properties of injective linear transformations. In this lesson we will show that injective linear transformations preserve linear independence, prove that an injective linear transformation cannot go from a higher dimensional vector space to a lower dimensional space, use this dimension consideration to conclude that some linear transformations cannot be injective, and learn that the composition of injective linear transformations is an injective linear transformation. Let's get started. First, let's prove that if you apply an injective linear transformation to a linearly independent set, then the result is again a linearly independent set. Our goal is to prove that the set of values is linearly independent in the codomain, and for this, we start with a relation of linear dependence on this set. Our goal is to prove that this relation must be trivial. First, we use the fact that linear transformations preserve linear combinations. If the value of t on a certain input is the zero vector, then this input is a member of the kernel of the linear transformation. But the kernel of an injective linear transformation is trivial. It contains only the zero vector. Therefore, the input vector must be equal to the zero vector. But now, the last equation is a relation of linear dependence on the original set of the domain. We assumed that this set is linearly independent. Therefore, all scalars in this relation of linear dependence must be equal to zero. But this means that the relation of linear dependence on the set of the values is the trivial one. Therefore, it must be a linearly independent set. But this is a result only in one direction. If the linear transformation is injective, then it preserves linear independence. Can we come up with an opposite statement? Yes, but we need to make our condition stronger. Namely, a linear transformation is linearly independent if and only if it takes any basis of the domain to a linearly independent set of the codomain. This is an if and only if statement, and we will establish two implications. In the forward direction, let's assume that the linear transformation is injective. Then any basis is a linearly independent set. And we just proved that injective linear transformations take linearly independent sets to linearly independent sets. It is the opposite implication that is new in this theorem. So, let's assume that the values of t on a basis form a linearly independent set in the codomain. We would like to show that this forces t to be an injective linear transformation, and to show that it is injective, we will prove that its kernel is trivial. Let's take any vector u in the kernel of t. Then u is a vector in the domain, and therefore it can be expressed as a linear combination of the vectors in the basis. Let's apply the linear transformation to this vector u. The result is the zero vector because u is the vector from the kernel. But we can also substitute for u its presentation as a linear combination of the basis vectors. T is a linear transformation, so it respects linear combinations. But what we have now is a relation of linear dependence on the set C, the set of values. And we assumed that this set is linearly independent. This means all scalars in this relation must be equal to zero. But then in turn, it tells you that the vector u is the zero vector. Recall that a scalar multiple of any vector by the zero scalar is the zero vector in any vector space. So, we proved that any vector in the kernel of t must be the zero vector. Therefore, zero vector is the only vector in the kernel. Therefore, the kernel of t is trivial. This means t is indeed an injective linear transformation. Next, let's observe that if we have an injective linear transformation from the vector space u to the vector space v, then the dimension of the domain u cannot exceed the dimension of the codomain v. This is going to be a proof by contradiction. Let's assume that the dimension of u is greater than the dimension of V. Also, let's call the dimension of U M and dimension of V T. Let's take any basis B of the domain U. It will have exactly M vectors. Then we are going to compute the values of the linear transformation T on each of the vectors in the basis B. This will result in a subset of the codomain V. We assumed that T is injective, therefore it takes linearly independent sets to linearly independent sets. The basis B is a linearly independent set, therefore the set of values C is also a linearly independent set. In particular, there could be no repetitions among the vectors in C, because if a set contains two identical vectors, then of course it is going to be linearly dependent. This means the set C contains m distinct vectors, so it is a set of size m. We have found a subset of the codomain V which is linearly independent, and the number of vectors in that set is greater than the dimension of this vector space. But this is impossible. You cannot have a linearly independent set whose size is larger than the dimension of the vector space. This contradiction was caused by our assumption that the dimension of U is greater than the dimension of V. Therefore, this is impossible, and we must have dimension of U no more than the dimension of V. We can use this result effectively to show that some linear transformations are not injective. For example, this linear transformation from the vector space of 2x3 matrices into C4 cannot possibly be injective because it goes from the vector space of dimension 6 into a vector space of dimension 4. Keep in mind, you can use this dimension consideration only to conclude that the linear transformation is not injective if the dimensions are not right. However, if the dimension of the domain is no more than the dimension of the codomain, this does not automatically make the linear transformation injective. Finally, let's prove that the composition of two injective linear transformations is an injective linear transformation. We already established that composition of linear transformations is a linear transformation, so the question really is about the injective property. Let's take two arbitrary vectors x and y in the vector space U. This is the domain of the composition of the linear transformations. If the value of the composition on x and y is the same, then it means s of t of x is the same as s of t of y. But s is an injective linear transformation, so if the values of s on two inputs, t of x and t of y, are the same, then the inputs must be equal to each other. But t is also injective, so if the values of t on two inputs x and y are the same, then the inputs must be equal to each other. But now, if you look at the beginning and the end of this development, this is exactly saying that the composition is injective. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will talk about surjective linear transformations. I will see you later.